everyone. This is the physical apparatus for the photoelectric effect experiment. Here, let's take a look at it. To begin with, we have the light source. This is a mercury arc lamp here that produces quite bright and it emits essentially white light at 5 or 6 different wavelengths in the visible part of the spectrum. Well, 4 wavelengths that we'll investigate today. Over here, we have the phototube, which is mounted in a housing. The housing shields it from stray light. It also shields it from stray electromagnetic signals. And we're going to connect our phototube to our external circuit through these 2 connectors, one for the cathode and one for the anode of the phototube. What does the phototube look like? Well, I can show one to you. It's hard to see the one inside of there with a video camera. But the phototube looks like this. Here, let me bring it a little closer to the camera. Okay? You can see here, it's a vacuum tube. There's a big curved metal plate, which is the cathode, the source of the electrons. And then it's a little difficult to see, but there's a narrow wire that's oriented vertically in the center, which is the anode. That's where the electrons would be collected. When light strikes the photocathode, electrons are emitted, and then some of those electrons make their way to the anode, and that current is what you're measuring in the experiment. Okay? So in our experiment, we'll do our measurements by connecting our phototube to a voltage source on one side and a sensitive current meter on the other side. And the current meter we'll use is this device. It's called a picoammeter. And it's a current meter that's specialized in measuring very small currents. Currents down to just a few nanoamps, or at the highest resolution, picoamps. Okay? Perfect. There are a couple more things we would have to add to do the experiment. Let me show you what these are. First, we're going to use a diffraction grating to divide the light from the mercury source into its component wavelengths. So the first thing we'll add is a slit to define the beam of light. So now light that has to travel through the slit to reach the source and detector. And then the second is this optic, which is a combination of a diffraction grating here, a transmission diffraction grating, and then on the other side, a lens. So, and we'll mount it in front of the slit in this way and adjust it to produce a focused set of, a focused pattern of lines over here at the detector, okay? I'll move this so you can see things in a moment, but I'm just going to set this here, and then we'll adjust this so that it's at the proper distance from the slit. 1 second. While I monkey around here. Okay. That's good, and let's lock it down. Okay. Okay, let's continue. I've just lowered the room light so you can more easily see the light from the mercury arc lamp. So now the light is going through the slit and then through the diffraction grating. And then the light proceeds over to our detector. Right now, the beam that we're looking at is traveling in a straight line from the mercury source to the diffraction grating to the detector. And we know that's the m equals 0 or 0 order mode of the diffraction grating. That one actually contains all wavelengths of light. But we expect that if we look off to the right or left side, we'll see colored light. That is the angle for the m equals +1 and -1 orders. The angle that the light makes depends on its wavelength. Here, I'm just going to rotate this to bring us over to the first order beam. The light's falling near the source now. It's a little hard to see for some reason on that screen there. It's easier to see on this box. You can see there are different colors of light going from yellow to green to blue to violet. And then there are a couple of other beams which we can't see with our eyes. We can't see them now, but actually you would be able to see them if they fell on a fluorescent screen on this. And those are ultraviolet emission lines of the mercury source. Okay? To do the experiment, we need to set things up so that one of these lines, one of these emission lines, proceeds to this screen, through an aperture in the screen, and then falls squarely on the phototube behind it. Unfortunately, you can't see the phototube inside the housing, but if you were standing in front of it, you would be able to, and you could align that, and then once it's aligned, there's a shield that will close to prevent stray light from entering this. Finally, one more piece of optical wizardry. The diffraction grating does a good job of separating the light according to the wavelength, but it's not perfect. So in addition, we're going to use an optical filter. We have optical filters here, what are called narrow band filters, for each of the wavelengths of the mercury emission lamp. And so this filter in particular only passes the green emission line of the mercury lamp. And if we place it in the beam, it will block all of the other beams. So that's with the filter in place. Here's what it looks like if I remove it. And so that'll do a good job of filtering out any stray light. It's actually easier to mount this on the detector housing than to mount it on the source. So that's what we'll do. Okay? Actually, with the filter on, things are so well shielded that we can turn the room lights back up. And that's what I'll do right now. Okay, now we'll talk about the electronics.